Hello and welcome to the Minnesota Homeland Security and Emergency Management's online training program, The Basics of Nuclear Power. Nuclear power is and has been an important source of energy for the United States since the first U.S. nuclear generating plant went online in Shippingport, Pennsylvania on December 2, 1957. Despite a more than 30-year halt in construction of nuclear power plants, the U.S. reliance on nuclear power continues to grow. For example, in 1980, nuclear power plants accounted for only 11% of the country's electricity generation. By 2009, that output had risen to nearly 20%. Much of that came from the reactors approved for construction that came online in the late 70s and throughout the 80s, which more than doubled U.S. nuclear generating capacity. Today, the USA is the world's largest producer of nuclear power. It contains 104 nuclear power reactors in 31 states. Nuclear power plants function in a very similar manner to that of traditional power plants, except that the source of energy comes from the splitting of the uranium-235 atoms instead of the burning of fossil fuels. There are three main areas in a nuclear power plant that we are going to discuss in this training: the reactor, the turbine and generator, and the cooling mechanism. The reactor vessel is housed in the containment structure. This is where the fission process takes place. During operation, reactor coolant water flows all around and through the fuel assemblies, removing the heat produced by the fission process, which creates steam. Steam from the nuclear reactor then travels through pipes and turns the turbines. The turbines then turn the generator to make electricity. The steam that turns the turbines is eventually condensed back into water and is used again. This is done by drawing in water from a nearby lake or river to cool the steam in a condenser. The condensed steam or feed water is pumped back where it is reheated into steam and is again sent to the turbines to make electricity, which completes the loop. The condenser water is then returned to the lake or river from where it was drawn. Although warmed by this process, the discharged water is not radioactive and is completely safe for the environment. Even from the earliest years of nuclear power generation, there has been a strong awareness of the potential hazards posed by a release of radioactive materials from a nuclear power plant. Of course, the main safety concern has always been the possibility of an uncontrolled release of radioactive material, leading to contamination and consequent radiation exposure off-site. These concerns are often capitalized on and perpetuated by Hollywood and the media, leading to misconceptions about the realities of nuclear power. The realities are this: there have been 3 major reactor accidents in the history of civil nuclear power: 3 Mile Island, Chernobyl, and Fukushima. These are the only major accidents that have occurred in over 14,400 cumulative reactor years of commercial operation spread over 32 countries. One of the common misconceptions is that a release at a nuclear power plant might look something like this. The truth is that a release like this is impossible. The reason is based on the ratio of the 2 forms, or isotopes of uranium, uranium-238 and uranium-235. It is uranium-235 that is used as a fuel in a nuclear power plant, but uranium-238 is far more common. Natural uranium is made up of only about 0.72% uranium-235, whereas the fuel pellets used in a nuclear reactor are enriched to about 3 to 4% U-235. However, to achieve a nuclear detonation that could produce a mushroom cloud, it would require about 90% enriched uranium. So there just isn't enough fuel in a nuclear power plant to achieve this form of nuclear chain reaction. In fact, if there ever were a release at a nuclear power plant, it would be completely invisible, and the only way to track it would be through the use of special equipment that is sensitive to radioactivity. At this point, you may be remembering back to the news reports from the disaster at the Fukushima nuclear power plant in Japan, where, through a series of events following the tsunami, an excess of hydrogen in the reactor building resulted in explosions on site. These were not the result of a nuclear detonation of the uranium fuel inside the reactor. These were chemical explosions caused by a buildup of hydrogen in the reactor building. This type of situation can occur if there is damage to the reactor core coupled with an inability to adequately vent excess hydrogen from the building. The Monticello nuclear generating plant is the same style as the Fukushima plant in Japan. So back in 1992, foreseeing such a possibility, Xcel Energy added a robust vent to the containment building in Monticello. This upgrade would allow for the ability to vent excess hydrogen to prevent it from exploding as it did in Japan. Because the primary concern at a nuclear generating plant is the radiation and radioactive materials involved in nuclear fission, nuclear power plants are carefully designed with multiple overlapping physical barriers to contain these materials. In addition, there are different styles of nuclear power plants. For example, the Monticello nuclear generating plant is a boiling water reactor, while the Prairie Island nuclear generating plant is a pressurized water reactor. As a result, there are various differences between these types of power plants that we should be aware of, including the ways they are engineered to generate electricity and the barriers used to contain the radioactive materials. A boiling water reactor, such as that found at Monticello, is a two-loop system. Water is boiled directly in the reactor vessel and converted to steam. As discussed earlier, the steam drives the turbine, which then turns the generator. Because the steam from the reactor has picked up some radioactivity and is directly used to power the turbines, some additional shielding is required in the turbine building. The other loop in this picture can be seen bringing in cooling water from the Mississippi River to the condenser. In a boiling water reactor, there are three primary barriers to radiation release. The first is the fuel assemblies. If we look closely, we will see that the nuclear fuel pellets are surrounded and protected by a zircaloy fuel cladding. The second physical barrier is the reactor pressure vessel, which surrounds the core and also prevents the release of radioactive material. If necessary, control rods can be inserted to stop the fission reaction. The third barrier is a steel containment vessel. This whole structure is then housed inside a secondary concrete shield wall, as shown in this cutout picture of a Mark I style boiling water reactor. A pressurized water reactor, such as that found at Prairie Island, is a three-loop system. In the first closed loop, water is heated to a very high temperature in the reactor vessel, but because it is under pressure, it doesn't boil and remains liquid. This heated water is pumped to the steam generator where it heats water in the second closed loop, converting it to steam, which is used to turn the turbines and generate electricity. This picture also shows cooling water that is being brought into the condenser from the Mississippi River. A pressurized water reactor also has three barriers designed to prevent the release of radioactive materials to the environment. And just like a boiling water reactor, the first barrier in a pressurized water reactor is the zircaloy fuel cladding that surrounds the fuel pellets. The second barrier consists of the reactor pressure vessel that surrounds the core, as well as the pressurizer and the steam generator. If necessary, control rods can be inserted to stop the fission reaction. Surrounding all of this is a very substantial containment structure which constitutes the third barrier and is made of highly reinforced steel and concrete. The entire structures of both boiling water reactors and pressurized water reactors are designed to withstand a multitude of natural disasters, including earthquakes, fires, floods, and the high winds and missiles that would occur with tornadoes. For an environmental release to occur, each of these formidable barriers would need to be compromised.